Voltage. In this video, we're going to talk about voltage, or the proper name for it being electric potential. They used to always use electric potential as it's associated with electrical potential energy, but voltage has become the regular way of referring to this, I don't know, sometime in the last 50 years or something. This is electrical potential energy is the field, or electric potential is the field for electrical potential energy. That means it's how much energy is a spot has the potential to provide without knowing what charge it's acting on. If we recall, electrical potential energy is KQ over R. So if we wanted to find something voltage, then what we're going to do is we're going to say everything about the potential energy is going to be specified except one of the charges. So our voltage is going to be KQ over R, and then we have our secondary equation to change voltage into potential energy by saying the potential energy is equal to the voltage times the charge. So the idea here is just like with a field, if we want to know the potential for an interaction, if we had a secondary charge, so if we, with the field, electric field, we would say the potential for a force to act on an object. Here we say the potential amount of energy that a charge would have in that location. Then voltage tells us that, and we don't have to know what charge it's acting on. This formula, once again, is for spherical charges, so we're imagining again that we have some spherical charge, and if we want to get a total voltage, just like with potential energy, we can just take the scalar sum of the individual voltages generated by individual point charges. So if I have something more complex, I can have like 3 point charges and come up with the total voltage at some location by simply adding the voltage created by the 3 charges. Okay, so the other thing about voltage to be aware of is it's a useful way to think about batteries. So for example, if we have a 9-volt battery, what we're saying is that we have the potential to provide 9 joules of energy if we allow 1 coulomb to pass through it. So imagine again, here's your battery. Draw it like a little 9-volt battery here. And if it's 9 volt, what that means then is that if 1 coulomb, so we're going to go maybe through a light bulb or something like that and then back in the other side. If we let 1 coulomb of charge pass through that battery, then the amount of energy produced would be equal to the voltage of the battery times the charge, so 9 volts times 1 coulomb, so 9 joules of energy. This is useful because when we have a battery, we know the potential for it to produce electrical energy, right? That's what that is. But we don't know how much electrical energy is actually going to be produced because we don't know what charge we're going to allow to pass through our circuit. That's why when we figure out the energy, I've been using U for energy, I'll stick with that. The energy, we need to know the voltage and we need to know the amount of charge. Or if we do the whole thing per unit time, so if I take the energy per unit time, then I get voltage in charge per unit time, which we more commonly think of as current. Then I get the power of an electric circuit is equal to the voltage times the current. So that's what voltage is. I'm going to do another video where you can see how you calculate it from point charges. On a battery, you can imagine that we have just set up the battery and measured that experimentally, but it is predictable, right? So then whenever you allow different amounts of charge through, you can predict how much energy you're going to create.